No, it's working. Okay. Yeah, I mean, yes. Okay. So finally, we are set for today's lecture. And if you remember, and I hope, sorry, it's up to you. Yeah. The last time we started with the data structures, and we learned that in order to work with our data, sometimes we need, I mean, not sometimes, often we need at least some data structure. And we have different choices when it comes to the data structure. So, for example, we can have a set, we can have a list, a linked list, queue, and we also learned about binary search trees. And we saw that each of these data structures, they have like kind of different characteristics. So, for example, some they allow us duplicate values, some they don't allow us, and some support the fastest get and access operations. In the some of them we have like every time when we add or remove, we have to shift the element. So that's why, depending on our application and the needs, we can choose a data structure that best satisfies our requirements. And continuing with the data structures, today we will be focusing more on the graph data structures. The graph is kind of like a more advanced form of a tree data structure that we learned in the previous lecture. And in the tree, we saw that the tree is basically a set of nodes and the edges between the nodes. And tree basically it's like a special form of a graph. Every tree is also a graph, but every graph is not necessarily a tree. And what's the difference between a tree and a graph is that basically in the tree we have like a root node, a node that doesn't have any parent. However, in a graph, we don't really need to have a specific root node. And another thing is that in a tree, we don't have like a cycles where a node starting point in a path is the same node as it is the ending path. If you have a cycles in your tree, then it's not a tree, then it becomes more like a graph. And also in a tree, we don't allow multiple paths between any two nodes. There will be only one path. And we have saw several different examples of a tree as well. And today, we will see that there are a number of different problems that actually relate, that can be modeled in the form of a graph. And the guys who work in a computer science domain or in a related subject, they have already defined a number of useful problem-solving algorithms for the graphs. So it means if we can define our problem as a graph, then we can utilize all those different algorithms that have been defined for working with the graph. And we will see how we can do that. So in simply, we can say that, as you can see in this slide, that graph is basically a set of nodes and the edges. The edges are like connection between the different nodes. And typically, by the nodes, we use the nodes to represent some data items, like the values you have. And the edges are the connection between the nodes we use to represent the relationships between the various nodes. So for example, here we have a graph that consists of 4 different nodes, A, B, C, D, and then there are several, couple of edges between those nodes. And we can represent a graph either in a graphical format, or we can also represent it in a set using the set notations. So as I said earlier, that as a computer scientist, we used to love the graphs, and you can see that there are a number of different scenarios where we are using either knowingly or not knowingly, we are using a relationship that relates to something like a graph. So there are some different examples. So for example, if we talk about the courses, and then we know that the courses that we study in our study program, they have kind of like prerequisites. And if we want to make sure that a student, whether to take a course, a student satisfies prerequisites or not, so we can define this in the form of a graph where the edges in between the different nodes. If you model your courses as a nodes, and then we implement the edges like a prerequisite. So you can, from one course, you can switch to another course if you have already studied or if you have already qualified that course. And similarly, if we see some more of the social media applications like Facebook, where you have a network of different friends or the communities. So every user in a Facebook social media network is like a node, and the friendship relationships, they are like edges. Similarly, we can say that the different bank accounts, they are like nodes, and the loans between one account or the transfer from one account to another account can be modeled as an edge. So there are a number of different cases that can be modeled as a graph. And when it comes to the graph, depending on the type of the edges that we use in a graph, we can have two different kinds of the graphs. So we can have directed edges. The directed edges mean that the edges that are pointing to some specific direction, so from A to B or B to C, whatever. So in that case, it's a simple concept. So we call a graph that has a directed with the labeled arrows. So we call it a directed graph. And if you don't have any specific directions, then it's like more like an undirected edge, and that kind of graph is called an undirected graph. So it can be seen like if we're talking about a map, like a Google map, where you have the cities as a nodes, and then you have the roads between the different cities as an edges. And we often see that some of the roads, they are like you can only transport or drive your car only in one direction. You cannot drive in the opposite directions. So this is something like directed and undirected. And sometimes we often use either a directed graph or either an undirected graph. But in some cases, you might have a problem that involves kind of a mixed graph, where you can have some of the edges are like directed edges, and some of the edges might be undirected. But that's only, depending on the needs you have. And then there are some like basic concepts about the graph. So we have like a path that is quite similar to we have a path in a tree data structure. So it's like path is like the sequence of edges from one node to another node. Okay, so if you have like 4 nodes, node A, B, C, D, and then there is a path from A to B, and B to C, and C to D. So that sequence of edges is called a path, and the length of path is usually the number of edges that are involved to make that path. And we can also compute the number of the length of a path by finding the number of nodes in that path. And if there are like 4 different nodes in a path, so its length will be number of nodes minus 1, because to connect 2 nodes, you don't need the 2 edges. Only one edge can be enough to connect the 2 nodes. And then we have an adjacent nodes. It's like a neighboring nodes. So and a node N1 is an adjacent node to N2 or any other node if there is a direct edge between those 2 nodes. So it's an important thing here to remember is that I'm not talking about the path, because if you are talking about a path, then a path could be having composed of more than 1 edges, and the edge is only when it's between one node to another node. And then sometimes we also have cycles in a graph. So for example, here we have an example graph that is composed of 7 different nodes, and we have labeled each of the nodes over there using A, B, C, D. And then there are like some edges going on. So we call a node a graph. So for example, we have some basic forms of the graphs that we call directed and undirected graph. In this case, the edges we have in a particular direction. So this is a directed graph. Okay, but then a directed graph could also be like a cyclic graph. Okay, we call a graph to be a cyclic graph if it contains one or more than one cycles. And how can you identify the cycles in a graph? The definition of a cycle is that a cycle is a path where the starting and the ending point is the same node. So for example, if you look at over here, if we see this is one path. We start from the node B, and then we end at the same node. So it's like a cycle. And it's also like if you see from here, starting from the node D, E, F, and then ending on the D, that's another cycle. Okay, and sometimes you can also have an edge pointing to the same node itself. That's kind of an edge is we call a reflexive edge. That also forms a cycle. So it means that for a cycle, the length of the path will be at least one or more than one. Okay, so and also we have another concept called a simple cycle, and then we have a cycle. And the difference between the two is, if you look at here, a cycle N1, N2, and N here are like the different nodes, is called a simple cycle if all the nodes in that path are distinct. And the distinct means that there is no duplicate. So what does it mean? Maybe it will be easier to understand it using this example. How many cycles can you see in this node? Can somebody help me? We already see two of them, like from B to D, and then from starting from the D and then E, F, and back to the D. Is there any other cycle in that graph? Sorry? E. What do you mean by E? You have to tell me like starting point and...
The E, the starting point, then goes to F, D, and then back to E.
Yeah, that's also another. And also, I mean, but in this case, if we see starting from the B and D, of course, I mean, the starting and the ending point will be the same, so we don't count it as a duplicate. We count it a duplicate. For example, if you start from here, B, D, E, F, D, and then all the way back to the B. In that case, D is not a starting point or the ending point. The starting and the ending is, we are starting and ending from here. So in this case, this is like a cycle. It's not a simple cycle. It's also a cycle, but the difference between the cycle and a simple cycle is that in a simple cycle, you don't have redundant or duplicate entries. All the if a node can appear only once on the path to that cycle. Okay, so and then we have some other terminologies, some basic other concepts about. Related to the graph. We have another type which is called a connected graph, and a graph is if there is if you have a graph that is consisting of like let's say 10 nodes, and if for every node in that graph there is a path to all the other nodes, then we call it a connected graph. So let's see if we look at the example over here in the back. So if you want to check if it's a connected graph or not, then you have to test it for every node, that from node A there must be a path to all the other nodes. So let's see, we have a path to the C, we also have a path to the B. We can, starting from the A, we can go to the D, and we can also go to the E, all the way to F and G. And then you also have to check from the G. Can we visit other nodes from the G? No. So then it means that it's not like a connected graph. So there is for the connected graph, there must be a path from every node to every other node. Okay. So in this case, the graph simply, which is not a connected graph, is a disconnected graph. Okay, and then we have a weighted graph. Sometimes when you have a graph, we normally in the graph we have the labels or the values associated with the edges. Okay, but sometimes we also want some information associated with the we normally have information associated with the nodes, not with the edges. Like the data values that we want to store in our graph data structure, we usually store them in the nodes. But sometimes, for example, we have a map about the cities. So we have information about the cities, for example, cities and the name of that city. But then we also have the information related to the edges. For example, the distance between the cities. Okay, so how far Kalmar and the distance between the Växjö is. So the city name will be modeled as a value in the node, and the distance between them is a edge property. It's a property or attribute that is concerned with the association between those nodes. So in that case, such kind of graph where we have values associated with the edges, we call them as a weighted graph. So every edge has some weight. Okay, if it's like depending on the units that you decide. So maybe if it's like the distance between Kalmar and Växjö is like, let's say 100 kilometers. So then the weight for that edge may be 100. And then we also have a multi-graph. The multi-graph is a graph. Usually we have only one edge between two nodes. Okay, but it could be like there can be more than one edges between the two nodes. So why we need this kind of like more than one edges? For example, there can be multiple relationships between two nodes. If you see the two implies, if the two implies may have maybe multiple relationships between them. They could be like colleagues in the same role, but for some other projects, they might be in some different roles. They might be like boss and subordinate, or maybe they could be like brothers. Who knows? And similarly, if we are talking about the cities, there may be more than one roads connecting Växjö and Kalmar. So you might have like, I don't know, is it 27 or 25, the Swedish national highways, or you can also, I mean, from, you can go from Kalmar first to maybe Emmaboda or some other city, and then from there you take another route, and in the end you end up, in such cases, a graph that has more than different edges between two nodes, we call them multi-graphs. Continuing with the terminology, so we also have in degree and out degree of the nodes. Simply, in degree is the number of incoming edges to a node. So, for example, if we see the graph, because this one is not actually a good choice to have a graph over here. So let's see, if we talk about the node D, and if we want to find the n degree of node D, simply we need to look at how many incoming edges are. So in this case, I think there are only like 3 incoming edges. So the n degree for the node D will be 3. And out degree for the node D is there are 2 outgoing edges. Okay, and we saw that I told you that in a graph data structure we don't have something like a root. Okay, instead we have a head and tails. In the tree we have like root and leaves. Root was something that doesn't have any parents, and the leaf was something that don't have any children. However, in a graph data structure, we have heads and tails. Head is a node whose in degree is 0, that doesn't have any incoming edges. So, for example, in this case, the node A doesn't have any incoming edge. So it's like a head node. We can call it a head node. And if we talk about the leaf nodes, sorry, the tail nodes, the tail are those nodes that don't have any outgoing edges, where the out degree is 0. So in this case, I think it's the G that doesn't have any outgoing edge. So the A is the head and G is the tail in that case. Yeah, so and then as we saw that in order to visit different nodes in a tree, we have a different tree traversal algorithms. We saw in the previous lecture that there was like depth first, and then we have a breadth first. And also we have like in order and pre-order, post-order traversal algorithms. When it comes to the graphs, we also have, because we know that these two are kind of related concepts. They have a similar terminologies, but there are also differences. So we have two major algorithms to visit the nodes in a graph. Breadth first, and then we have a depth first. As the name indicates, like the depth first is where we go deeper and deeper. So we start, there is no, I mean, in the graph we don't have any root node. In the tree we have a root node, and we often start an algorithm from the root node. So, but in the graph we don't have like a starting point, so you can start from any node that you want. Maybe for some algorithms you can start from a head node, but there can also be more than one head. So then it's up to you. I mean, you can pick any starting point, or maybe application specifies you that you should always start from this node. And then we have a breadth first. So in the breadth first, it's like we visit more on from the starting point. We, instead of going deeper and deeper, we first visit the node at the same level. Instead of visiting a node and then visiting the child or the successors of that node, we first visit the siblings or maybe the adjacent nodes to that node. So if we starting with the first simple algorithm, depth first search algorithm, and I think the assignment 3 also involves the implementation of this algorithm, so it's also important from that point of view as well. So here we have a simple algorithm specified. So as I said that there is no root node, so you can choose a starting node n from your graph, and then what you need to do is that you need to mark that node that you have already visited it. Okay, and once you have marked it, then you have to, for each of the successors, and the successors are like the nodes that are following that node, okay, next to that node. So for example, it will be a bit easier if we see the example over here. So let's say here we have this depth first search algorithm, okay, and our starting node n, for example, I say that we start from the node A, okay, and then the algorithm says that mark n as visited, okay, it means that we have already visited it, and then for each s that belongs to the successor of n. So in this case, C and B are the successors because they follow, they come after A, okay, and then we check if S not visited, if you have already not visited, because there can be loops, cycles in your graph. It could be that you have already visited that node. So if you have already visited that node, then you don't need to visit it again. Okay, so before visiting a node, you must have to check that. If it's not visited, then you have to recursively call depth first search algorithm on that. So for example, we start from here, A, okay, we mark it visited, okay, you can use some flag, some kind of value that you have already visited this node to make sure that you don't visit it, or maybe you can add it into a set And if you try to add the same element again in a set, that will not be allowed. Okay. So, and then you can either go this way or you can go either this way, because there is no restriction. It says that for each successor S that belongs to the successor of n. So let's say we start from the node A, and then we first visit A and mark it as a visited, and then we go to the C and call this algorithm DFS on that node S, successor of our starting node. On C, we again do the same, because when you recursively call the algorithm, so your control will go back to the starting point of your method. And now in this case, the n becomes C. So we mark C as visited, okay. And then for each S that belongs to the successor of, now the n is C. So what are the successors of C? C has only one successor, which is D. And we check if D not visited. Yeah, D has not visited. We have only visited A and C. So then it's okay. The condition is true. We call it DFS on the node D. And on the node D, okay, we mark it as a visited. And then how many successors D has? D has two successors. It has a successor E and also B. So it's fine, either you pick this or B. You can start with any one. So in this case, let's say we take the direction this one, E. Okay? And we check it if E not visited. Yes, we are until here, and E has not been visited before. So we call this method again, and for each S that belongs to the successors of E. So E has two successors, F and G. Okay, we can take any one. You can take G or you can take F. So in this example, I take F. Okay, and I call this DFS algorithm recursively on with the node F. When we go on node F, when we call this F, mark n as visited, so F has been added. And now if I go here, for each S that is successors of node F, what are the successors of node F? F has only one successor, which is D. And then we check the condition. If D not visited, that condition now should be false, because we have already visited the D. So in that case, this will not be called, and our control from, instead of going here, control will come back to E, because when you are calling the method recursively, it should transfer your control back to the method from where you called it. And in the E, we have two successors of E. F, we have already visited F, but we have not visited G. So then it will call on the G. And on the G, we mark it after the F with G, and then we check for each S that is a successor of G. However, G doesn't have any successor. Okay, so we don't need to check for the G. In that case, the control will go back to E. We have already visited all the successors of the E, so there is no more left. So we go back onto the D, and then on the D, we have visited E. However, we have not visited B. So then we will call the method recursively on B, and on the B again we call for each successor that belongs to the B, and B has only one successor, which is D. However, we have already visited D, so we will not call the depth first search on D again. In that case, it will return back from where it comes, from the D. And in the D, we have already visited all the successors. It has only two successors, E and B, but both have been visited. So we will go back to C. And in the C, we will see that C has only one which has been visited. So we will go back to A. And on the A, we will check successors list. A has two successors, C and B. However, we have visited both, because we have visited B from the D. So it will come to and end after visiting the B. So there will be no. So in that case, we have visited all the node using the depth first search. However, if we start, in this case, we started from A. We visited all the nodes. But let's see, if you start from the road, if you have picked the D as a starting point, in that case, okay, we are starting from the D, and we check what are the successors of the D. We mark the D as a visited node, and then for each S that belongs to the successor of D, because N is now D. So D has two successors, E and B. You can choose whatever path you want to go. So I selected E, and on the E again I check the successors. It has two successors, F and G. Okay, this time I decided to go the G way first, and on the G I check G doesn't have any successor, so I will go back to E, mark it as visited, and then for the other successor F, okay, I mark it as a visited one, and then for the F I check if F has, for each successor of F has a successor D, but that has been already visited, so I don't need to call it again. So I go back to the D, and then D has another successor which is B. I will visit it because I have not visited it already. And on the B, I will see what are the successors. The B has successor D, and that has been visited already. So starting from the D, I can only visit D, E, G, F, and B. I will not be able to visit C and A. That's another example of, it means that this is not a connected graph because there is no path from D to C and A. Okay? So it means that if you are using a depth first search algorithm on a directed graph, then you are not there is no guarantee that you will be able to visit all the nodes. If you want to visit all the nodes, then maybe you have to call that method again on some different node until you have visited all the nodes in that graph. So for example, if you want to use the depth first search algorithm and you want to visit all the nodes, so after you have started with the D and you visited these nodes, and then maybe you see that in that graph you have A and C. So you have to call that algorithm on some of the node which has not been visited before. So you can call it maybe on A or C. Okay. So let's say in this case, after visiting with the D, I call it with the node A, and in this case I will visit A and C. We don't visit the other nodes because the other nodes have been visited already. Is it okay? So why, then the question is, I mean, of course, when we're talking about the algorithm, and in the beginning I told you that if you have a problem and if you can model that problem in terms of a graph, then you can take advantage of various graph algorithms that have been defined for the graphs to solve different kind of problems. So for example, what kind of problems you can solve using this depth first search algorithm. So if you want to find out what are the reachable nodes, reachability of some node, obviously you have already seen the example. If you have a graph of like 100 nodes, and if you want to find what are the reachable nodes, what are the if there are like if Växjö is a city and that is modeled as a node in a graph with the different roads connecting to different cities, and if you want to find out to which other cities we can travel from Växjö, then you can use the DFS, and then if you start with the node representing a Växjö, you will find all the reachable nodes using the DFS. Okay. We can also find cycles in the graph that we will see in the coming slide, that how can we use depth first search algorithm with a slight modification to find out, because I mean, of course, if you have a graph modeled on a picture or on a whiteboard or on some diagram, you can see with your human eyes that there is a cycle. However, for a computer, it's not easy to find a cycle just by looking at a graph. So you must have to have defined some properties, and based on those properties and those values, it can find identify. You have to define some theory like, okay, what will be the value, or what conditions. If these conditions are true, then it's a cycle. If these conditions are not true, maybe then it's not a cycle. Okay. So, and then also topological order. So we will see what are these topological order thing is. A similar concept which is related to the depth first search algorithm is post order traversal. It's basically, similar in nature to the depth first. The difference is in the depth first, we start from some node, and then we go deeper and deeper and visit its all the reachable nodes from that node. But in the post order, the difference is we start from some node. However, we post. In our list in the visit, we don't put it in the front. We visit all the deeper nodes, all the downwards, all the successors, and after visiting all the successor on the deepest level, we visit the starting node. Okay, so let's say let's see if we have an example over here. Yes. Here we have an algorithm for the post order traversal. So for that we need two input parameters, some starting node and a PO list, post order list. A PO list is like it's like the sequence of nodes in which we visit the nodes in the post order. Okay. Also, for both depth first and post order, it's important to have depth first, starting node from where you start, and also depending on the path that you choose, you can have different depth first orders. So, for example, if we look at the depth first example over here, I started from A and then I go to the C, and then, but instead of going to the C, I can also go to the B first. That's absolutely fine, because according to the algorithm, I can pick any of the successors. And if I pick the B, maybe then I will have go first to the D, and then after visiting the nodes, I will come back to the B. So similarly, in our post order, there can be more than one different post orders depending on the path that you select. So often when we are talking about the post order, we first need to identify which path we are taking. So for example, if we take this path A, C, D, E, F, G, B, it means that we're starting from the node A and then we go to the node C. Okay, and then if you see this algorithm, it is almost the same like we have for the depth first. In the depth first, we also mark n as visited, and we check that for each s that is successor of n, we do if s not visited, then. However, the different thing over here is that we are maintaining a post order list. And the post order list, why we are maintaining the post order list? Because using the post order, we want to visit the successors first. Okay, so instead of visiting the starting point, we want to visit the nodes in a post order where the things are done in the end. Okay, so we started from the node A and we check mark n as a visited. Okay, we mark A is the starting point, and I marked it as a visited, so I have already visited it. That's fine. And then, if we are following this path, I go to, for each S that belongs to successor of N, I take C because C is a successor of A, and I check if C not visited. C is not visited. Yes, that condition is true. Then I call this algorithm post order on node C. Okay, and PO list in this case is empty. I have not added anything in the PO list, so it's like an empty list right now. Then I go with the node C. I come to this condition, mark N. N is now C as visited, so I visited, mark it as with some flag, so it's visited now. And then for each S that belongs to successor of C, so C has successor, only one successor, which is D. So, and then if D not visited, then I call this post order method again. Now the S is D. Okay, the argument for the S is D, and the PO list is still empty. We have not added anything. Then I go to the each successor of I mark the D visited. In each successor of D, I take E as a successor, and then I check again if E not visited. Yes, E was not visited, so I mark I call this post order with the attribute E, and then PO list. Okay, and on this E, mark N as visited. Okay, this has been marked visited. For each S belongs to the successor, again it has the successor F and G. Okay, I take this way, and I take the F, and I call post order F PO list, and then I go here, mark F as visited. Yes, this has been visited now. And for each successor of F that belongs to this, so what are the successor of F? It has a successor D. Okay, and I check if S not visited. D was visited already, so in this time this condition will be becomes false. I come outside the loop, and in the outside I use post order numbering, just a counter. Post order numbering is like the order in which you visited. Okay, which node you visited first in the post order. In this case, like the counter was like initially with a 0. However, now the counter will become plus plus, like so. And this N, what is N over here? F. And the post order number for the F will become 1. So it means like I visited F at first. Okay, and then in the PO list I add N, F, and the value for the post order numbering F gets 1 from this part. Okay, so it means that simply I can explain this again, but it's not very complex. Simply starting from the A, C, D, E, I visit first the F, and then because D was already visited, it doesn't have any more successor. We cannot go any deeper further, so we go back. Then we find G. It's a deepest one, so we visited it again, and then we go back E. E doesn't have any successor. D, yes, no. D has a successor which is B. Before visiting the D, we have a successor which is B. Okay, so B, D, C, all the way opposite. So we first visit the successors are the deepest nodes, and then in the end we visit the predecessors in the post order. So the difference between depth first and post order is, in the depth first we visit predecessor first and then the successors. But here we are first visiting the successors to the deepest level, and at the end we are visiting, after visiting all the successors, we are visiting the their predecessors. Okay. So simple to remember that in the post order we have a last action in a recursive depth first traversal. This whole algorithm is same like a depth first, but we are doing some before returning the method, we are doing some processing. We want to do some actions, and the processing that we are doing is, we are assigning the nodes, and we are assigning the nodes to a list, and we are assigning each node a number, which is a post order number. And now, if you see, we have, using this post order algorithm, we have assigned every node some number, which is a post order number. Okay? And now we can use this post order number to find out if we have cycles in our graph or not. And how can we do that? Normally, if we have, here we have a definition for a forward edge and a backward edge. How can you find out? I mean, if I don't, I can see from here, if A is our starting point and B is our ending point, I can see that this one is a forward edge because it's moving something in a forward direction. It's not moving in the backward direction. But how computer will visualize this? Okay? For this, you need to define some theory, and the theory for that is we call an edge as a forward edge when the post order for the source is greater than the post order of its target. In this case, if what is the post order of A? For this edge, source is A and target is B, and we can see from here the post order number for A is 7 and for B is 4. So 7 is greater than 4, it means it's a forward edge. And if we talk about these two edges, B to D, in this case B is the source and D is the target. What is PO number of B? PO number of B is 4 and D is 5. So in that case, is it a forward edge or is it a backward edge? If the post order of source is greater than of the target, then it's a forward edge. Otherwise, it will be a backward edge. So in this case, this edge is a backward edge because the post order of B is less than that of D. Okay? So it means that using the post order, we can find whether an edge is a forward edge or it is a backward edge. And if your graph contains one or more than one backward edges, then it's a cyclic graph. Also, maybe we can also find out from here, F and D. What is the post order for the F? The post order for the F is 1. Okay? So the source is 1 and target is D is 5. Again, the post order number of source is less than that of a target. Is it clear? So it means that if you have a graph which has a cycles, and you need to, if you have an some application that is dealing with multiple graphs, where some of the graphs are cyclic and some are not cyclic, and if you need to classify which one are cyclic and which one are not, which one are acyclic, then you can use PO, post order algorithm, to identify the backward edges, and once you have identified the backward edges, you can classify if a graph is cyclic or not. Okay, so we have saw some of the backward edges here, and then there was like question, can you find any other backward edge? Anyone? Yeah, I think I already told you F to D. Okay. So and the simple thing is, I already told you that if a graph contains a backward edges, then it's a cyclic graph. Next, we have a topological order. Okay. And the definition for the topological order is it's an order of the nodes such that each node appears before its successors. Okay. So what does it mean? That if you have a graph and if you want to visit the nodes in a way that before visiting the successors, you must always visit the node itself, because in the post order we are first visiting the successors, we are not visiting the node itself. However, if you want to visit the nodes first and then its successors are the descendants, so this kind of order we call it topological order. And if you see that, it's actually a opposite of the post order. If you have find a post order and if you sort it in the reverse order, you will automatically get topological order. So once you have a, but then the important thing is that if you have a graph which is a cyclic graph, for the cyclic graph, you cannot find this topological order, because for the cyclic graph it's hard to define which one is the predecessor and which one is the successor, because they have a cycle. For one node, for one edge, maybe a node is a predecessor, but for the other edge, the same node will become a successor. Okay, so the first condition is if you have to find the topological order, and I think that you also have a one task in assignment 3 that requires you to do this topological order. So to solve that problem, the first thing you need to do is, if you have been given a graph as an input, you need to check whether it's a cyclic graph or not. If it's a cyclic graph, you can simply set it, tell that the topological order is not possible. If it's otherwise, you can use the algorithm for the post order, and once you have found the order for the post order, you can just reverse it to find topological order. Simple as that. Okay. And then we have the breadth first BFS algorithm. However, I think before starting with the BFS, let's take 10 minutes break, and we continue after that break. Okay. Okay, I think it's time to continue with the remaining part. And the next traversal algorithm, we have a breadth first, and opposite to the depth first, where we first go deeper and to this all the successor nodes till the tails. Here we start from whatever node you decide, and after visiting that node, you go to its successor node. However, from one successor going all the way down to the leaf, to the tail nodes, you first visit its other successors of that node. So, for example, if I show you an example over here, so let's say if we start from an A, and in the depth first we was going from C, D, E until there was no further successors of a node, until we ended up with some of the tail nodes. However, in the breadth first, we start from a node A, let's say, we go to the C, but before visiting the successors of that node, we first complete all the successors of the node from where we started. Okay? From C, we will visit B first. And once we have done with the successors of A, then we can pick any of them, C or B, and then we visit all the successors of C and the D, then we go all the level down. Okay? So that's like you complete more on a top level until you go to the lowest level. And the algorithm we have over here. Okay? So, and it says that choose a starting node N that belongs to the node set of nodes, and mark it as a visited. Okay? And then after marking it as a visited, you create a new set. Okay? And the first set that you create, let's say we call it set 0. Okay? And you add that node which you have visited to that set. So, for example, if we have started our breadth first from the node A, okay, so we mark A as a visited and added it to the S0 here. And after that, we call DFS algorithm on this set S0, which is our starting set. And in this case, where BFS is a method, and this method definition is given over here, okay, which takes an input parameter of type a set type parameter. Okay, in this case, S0 will be passed here, and in that we create a new set. If we started from the S0, so the next set will be our 0 plus 1, which will be set S1, and in that set we add for each n that belongs to the successors of that belongs to the member of that Si. So, in this case, Si was S0 and it contains only one, which is node A, and then for all the members that belongs to that set, we visit its successor nodes. Okay? And then we check if S not visited, mark it as a visited and add it to that set that you created as a new set. So, for example, if we have called this method with S0, S0 is A, and then we check it over here, for each n that belongs to S0, it has only one, which is A, and A has two successors, C and B, and we check if C is not visited, okay, we add it to this new set, which is S1. S1 initially will be empty, but then you add the successors of A into that, B and C, before going to the next. Okay? And once you have visited all the node, okay, you completed it, and then we call this BFS on this new set that you have created, I plus 1. So, I was 0, now you call it on 0 plus 1, which is 1. So, as on this. Okay? And then you will go again and check for each element that belongs to this set. Okay? You do it like this. You check on you add its successors to a new set S2. In this case, C has the same successor, B has the same successor. So you will not, if a successor has been already visited, you don't need to visit it again. You don't need to add it again. Okay. So and in that way, after D, you will check what are the successors of D. D has successor E and B. However, we have visited B already, so we don't visit B again. We will add only E to the new set. And in the E, we check its successor, which are F and G. And we add them because both of them was not visited before. So we add them to a new set. And then we check successors of F and G. G doesn't have any successor, so there is no question. F has a successor D. However, D has been visited already. So in that way, we will get this order A, B, C, D, E, F, G as a result of this breadth-first search algorithm. And if you start, instead of starting from A, if you start from some other node, let's say D, in that case, you start with a D. In this case, your S0 will have node D, okay? And then you check what are the successors of D. D has two successors, E and B. Both of them has not been visited before, so you will add them both to the S1. So S1 now has B and E. And then we check for both of them, like for the E, what are the successors? E has successor F and G. Both were not visited, so we add them into the new set. And then for the B, B has a successor D. However, D was visited before, we don't need to visit it again. Is it clear? And next, we have an algorithm with the name of transitive closure. And the transitive closure is if for every node in your graph, you want to find what are the reachable nodes. Instead of finding a reachable node, set of reachable node for one single node, you want to find the reachable node for all the nodes in your graph. And we know that how can we find the reachable nodes? Which algorithm we can use to find the reachable nodes? Can we use post order, or can we use depth first or breadth first? Which one? We just learned a few minutes ago. We can use depth first, okay? We can use the depth first to find out, and if we use the depth first on every node in your graph, and then the order it runs, if we store it as a list, you can get the transitive closure for your node, okay? So the algorithm for it is quite simple. For each node n that belongs to your set of nodes in the graph, you call DFS algorithm on that node, and the output that you get, you store it in a list. And in the end, you will get, you can use your some of the hash map or map table hash map or hash set for this kind of algorithm, okay, where you store the list. Because, I mean, why we are using the list here? Because as a value, as a key value pair, you don't get a single node, but you get more than one nodes that can be reached from one node to another, to other nodes in your graph. Is it clear? And then we have a concept like graph partitioning and connected components. We already saw that a graph can be either a connected graph or a disconnected graph. What was the condition for the connected graph? It was if for every node there is a path to all the other nodes, okay? And if you don't have a path to all the other nodes for each node, then it's not a connected graph. And we saw the examples of that already, okay? And if and this concept of connected graph give us the related concept of partitioning and connected components, okay? If for some of the graphs, maybe you have only one connected component, but there can be a graphs where you have more than one connected components. And what does I mean by connected component? Connected component means like starting from one node, the maximum node that you can reach from that node, okay? So for example, if we take an example, let's say, yeah, if we look at here, what nodes can we reach from? If we start from here, E, we can go to F, we can go to G, and we can also go to the D, we can go to the B, but we cannot go to the C and A. Okay, so it means that this is one component, and then maybe A and C can be another component in your graph. And sometimes we also call these, in some of the literature, we call these different components in your graph, we call them partitions. Okay? And for the partitions, there are some conditions. So for example, we can call, if you have a graph, G n of E, where n is the set of nodes and E is the set of edges. And if you have more than one such node sets, S1, S2, SR, then if you have these conditions true for those set of nodes, then you can say that those partitions or the components of the graph are legal partitions. And what are these conditions? The first one is quite simple, that none of that partition or connected graph should be an empty graph. There must be at least one or more than one nodes. And then there cannot be one node can be only in one partition. You cannot have a node in more than one partitions. Okay. So if you have this three, let's say if you have three partitions in your graph, and if you take a union of those three partitions, then you get all the set of nodes that you have in your graph. Okay. And also there must be no overlapping. What does it mean by that? If you have a node in one partition, then it should not be existing in another partition. And then we have a algorithm. If you want to find out, it's more like a pseudocode that you can maybe use it to write your own code. And what does it say? If you want to find out what are the connected components in your graph, you can start by keeping each node. So let's say if you have 5 nodes in your graph, okay, you can start by putting all the nodes in a different sets, and assuming that each node belongs to its own partition. Okay, and then you check the edges between those graphs. For each edge, here U is like a source node and V is like a target of the graph. If U and V belongs to the different connected components, if they are not part of the same, because what is connected component? Connected component initially will have U and V in a different, because we're starting with all the nodes to be in its own connected component set. Okay, if they belong to the different sets, however, because we have an edge, and edge means that these two nodes are connected, they are not separated. And if there is an edge between two between two nodes, then they should be merged or put in a same partition instead of putting them in a separate partitioning. Okay, and once you have done with all the edges, in the end you will get all the partition that remain will be the possible partitioning for that graph. Okay, so this gives us an end to the various graph algorithm that we have. Next, we have a quick overview for the assignment 3. I think you have already saw it. It has been posted on the course home page. So basically, in this assignment, you have 3 different parts. 2 of the parts they are like requiring you to implement a graph and some of the graph algorithms. And to implement those algorithms and the graph, we have provided you with some basic code in the form of interfaces and abstract classes. And we want you to implement those classes and interfaces. And I will give you some quick overview, and maybe after the lecture, Charles can give you more details. And if you have questions which we expect to have, then you can discuss with him. As I said, that in the part 1, you have basically 2 interfaces. One is the interface, another one is actually an abstract class, and you need to implement them. And we also provided you with some JUnit test cases. And it's very important that when you are implementing them, you make sure that your implementation is passing those JUnit tests, because that's kind of like a prerequisite. We will consider your submission only if it passes those JUnit tests. If your submission doesn't pass the initial, it's like initial screening. So if it fails to pass that test, we will not bother to look at in your code. And then there will be this algorithm that we talk about. GML graph modeling language I will talk about in a short while. But we have already saw the other algorithm that we require you to implement. And yeah, and its third part is about time complexity, which we have not covered yet in this lecture, but we plan to do it in the following lecture. So how can you estimate the time efficiency of your implementation? So we basically require you that the code that you implement for the algorithm, then you should do some theoretical computations, like how much time your algorithm will require depending on the input size that we give. Some basic facts about the graph interface. It's a basically directed interface, interface for a directed graph. And yeah, you have a node class, abstract class, which represents the nodes in your graph. And in that graph, we require you that the graph should not have two nodes which are equals. So if a node has been added already, it should simply ignore it or give some kind of exception that the node is already added. And multiple edges are not allowed. Okay, so if there is already an edge between two nodes, then you cannot add a new edge. And yeah, and there is no specific class for the edge. Of course, sometimes you can implement the edges using a separate class, but in this case, we assume that you can maybe maintain a list of predecessors and successors, and then you can use that list to traverse as an edges. Okay. And with the assignment description, we have given you some Java docs that you can read about more, that what a method in a class is doing. For example, add edge for, so you can read about that. What are the parameters of this method, and what should it return? So, for example, this method provides you functionality to add an edge. It takes two input parameters, from node and to node. So basically, it takes two node type parameters, and then if the edge has been created successfully, then it should return true. Otherwise, if, for example, if the node doesn't exist, or if there happens some problem, it should return false. Okay. So it's quite important that you go through all these API details and implement the methods accordingly. And here is just a simple overview of the graph, the different methods that we have in the directed graph. And you can see that we want the graph to be a generic one that can be used with the different data types that can be instantiated at runtime. Okay, so add node, as I said, that it takes a generic parameter and create a node for that and add it into the graph. And yeah, you can use this method get node to get a node for the item that you pass. Add edge, yeah, I already talked about that, contains to check whether this node exists in your graph or not. Node count should return the total number of nodes. The methods are quite self-descriptive, but you can use the Java docs to find more details. And here is just sample code how your implementation can be used, for example. And we require that the classes that you implement, we have already given the naming instruction that you should have the class that implements this directed graph interface should be named as something like my graph. Okay. So, and in this way you can create because the implementation that we want should support generics. So I want to create, let's say I want to create a graph for the integer type of values. So I can use it like this, and then I can call the add node for methods and provide some values, integer type values, which are being stored in an array. So by these three different lines, add node for I0, I1, I2, it should add 3 nodes in the graph. So basically, these lines they will only add the nodes. They will not add any edges between them. And if you want to add the edges between them, you can call add edge for method. And here I0 is like a source, and this is like a target. So these 3 lines will create 3 edges between 0 and 1, 0 and 2, and 1 and 2. Also, this add edge for method has a special feature. For example, if a node is not, now we have created 3 nodes with value 0, 1, and 2. But if you call this method with the node value that is not already created, then it should create a node for it. Okay, and that's given in the method instructions. If you call a method add edge for with a node which is not already created, then it should also create the node and add it to the graph. And simply you should also have a toString method for that graph that should return a string representing the graph in some format that can be understandable. That this one is a node, and this node is connecting to these different edges. And then you have also abstract node class, okay, and it also have a similar kind of a methods. So let's say has successor, yeah, it should return whether this node has any successor or not. If there is a successor for a node, it should return true, otherwise it should return false. And in degree should return the number of incoming edges, and the out degree should return the number of outgoing edges. Has reflexive edge means like where the source and the target are the same. Okay. And here is some of the hints. Yeah. So maybe it can be used as a starting point, but it's not really necessary that you implement it like this. You can, of course, implement by your own way. So as I said that we use instead of using the edge class, I mean we have used predecessors and the successor. So in this case, if you look at the code for node class, the node abstract class here. So there is in the abstract class that we provide to you, there is nothing that models predecessors and successors. So it's only the item, the value that node should have is defined over there. But if you want to maintain a list of predecessors and successors, then maybe you need something like a linked list or maybe a hash set, I don't know. So to keep track of what are your predecessors and successors, okay? Because for every node, a node should be aware of what are its predecessors and successors. And yeah, and if you want to add successors, if you have something like a list, then you get a values, the node as a successor, and you can call the add method on that list to add a successor node. So you can use, as I said, you can use this as a starting point, but of course you are free to choose your own way of implementation. And similarly, I provide you some basic code for graph implementation. Okay, I use a map. It could be a hash map for the nodes and to keep track of the values. But you are free to use any other data structure. There is no compulsion. And I also maintain head and tails, so you can maybe also maintain head and tails to know what are the head nodes in your graph and what are the tail nodes in your graph. And from that you can also use because there are, if you look at the interface for the directed graph over here, it has methods on the heads that returns iterator if you want to traverse the head nodes in your directed graph, and also for the tail. So in that case, if you have these kind of attributes, it will be maybe quite simple for you to iterate on the head and tail nodes. Okay, and then the last part we have the GML. It's a graph modeling language. So basically, I mean, when we draw graphs, we usually draw them graphically using some circles, squares, and the lines between the nodes. However, in terms of the computers, that representation is usually stored in terms of some data values. Okay, but if you want to, if you have generated, if you want to use a graph in your program, and later on, like an HTML, where you write a code, but then that code can be formatted, and you can type format like LaTeX or other type formatting languages. So similarly, you can use GML to model, to write a code or maybe text, and then you can use some GML interpreter to interpret your code or your lines of instructions to generate a graph. And I recommend to use a tool with the name of YED, and here is the link. Let's see if it works or not. But let's see, we can, I think, find it over here. It's a quite nice tool to draw the graphs, and you can also, use its online version, or you can download and install it. So let's say I have here already installed on my system, and this is how your GML files looks like. We basically we start with the graph keyword. Sorry. Yeah. You should have pointed out quite earlier. I was like, So in the GML, we have, if you want to define a graph, you use the graph keyword, and then you use the square brackets, and to define the nodes, we have this node keyword, and then every node will have some ID that you can define with this keyword ID, and then every node can have a label, and you can also define the colors and the type, like rounded or maybe square. And after you have added the nodes, you can also use the edge keyword to define the edges between the nodes. And if you want to create an edge between the node 0 and node 2, so you can define source 0 as a source and node 2 as a target. And then also you can define the type of the node, like a directed or with the arrows. So, and I recommend that, it's not a core part of this code. It's more like a kind of something like supplementary thing that you can use to visualize the graphs that you create with your code. And this is again here, like how this your GML file should look like. And so let's say, and also it's also important that, let's say, I don't know if it's Shalos, have you used this tool before or not? Yet? Okay. So then maybe I have not used it myself a lot. So maybe you know this better than me. The thing is, one of the problems that I saw, maybe I don't know if it's just on my machine or if it's on all the machines. So again, I forgot that thing. So when you use this, like for example, if you want to open it on some of the files, like I already have some GML files over here, and let's say if I try to open this cyclic graph, it only shows me just a single node, okay? And then I have to go to the layout, and then I have to select some appropriate layout for that, and then it goes like this. It's also the same for you? Okay, then it's maybe something tool specific. Yeah, and why this is important for you, because in the assignment, I think in the part 2, we have given you this GML interface, and in this GML interface, we want you to implement this toGML method, okay? And what should this toGML method should do? It should, if you have a graph over here, and if you call that toGML method on that graph, it should write the GML code for that graph. And what does I mean by the GML code? Is something like this. It should take a node, and for every node, it should write something like this. And for all the edges in your graph, it should create and save that file with the extension .gml with some suitable name for that graph, and okay. And then if you want to see that how does your graph looks like, then you can use the jet tool on that GML file, and you can visualize it, whether all the nodes are over there or some edges are over there or not. Because when you will be implementing the other, let's say, some of the other connected components or other algorithms, so in that algorithms, maybe you need to visualize the graph that you create. And in that case, tools like jet can be handy to visualize something, because if you have something like this, it's maybe easier for computer to compute and work with, but not for you as a human. Okay. So, and this brings to the end of today's lecture, and here are some suggestions. And the next time, in the next lecture, we will talk about the focus will be more on the algorithm and what are the important factors to design an algorithm. Okay, so some basic stuff about the algorithms and more about time complexity. Okay, so if you don't have any question, then I say, yeah, you have a question, yes?
I have a question about the assignment.
Which one?
The final one.
The third one, or you mean final fourth one?
The written exam.
The written exam, yes, yes.
So, I don't understand the process. What do we do? Do we have to register somewhere?
I think I already uploaded the information on the page. So you are a campus student, and you should do like usually you do for the other exams. This is
our first one, our first written exam.
Okay, that will be your first written exam. Okay, I think on the LNU web, if you go to the My Pages, you can find.
There, but don't really. It takes me when I click on the link, it takes me back to LNU unless I'm.
Okay, maybe Charles can take a look with you during the labs. I actually today planned to take, usually I was taking a train at 4. I think that goes at 3, 6 past 3. So it's already 12 minutes to go. So I will be running, but I mean, because that's not something a serious problem, I hope you will manage it. Yeah.